In the previous chapter, we introduced a way of grouping brain structures according to 4 discrete areas: the brainstem, the cerebellum, the diencephalon, and the cerebrum. In this chapter, we will focus on the 4th of those areas, the cerebrum. The cerebrum consists of 2 hemispheres, the left and the right. Now, in general, the left hemisphere controls the right side of the body, and the right hemisphere controls the left side of the body. We call this contralateral processing. Now, the fact that the cerebrum consists of 2 hemispheres is actually the origin of one of the biggest myths in education in relationship to the brain and learning. That is, the idea of left brain versus right brain. This is a pretty common myth, and you've probably encountered it at some point in your career. The problem is that although it's true that the left hemisphere and the right hemisphere do have some structural and functional differences, in reality, even for the simplest of tasks, you require both hemispheres to work in coordination. The cerebrum, like the rest of the brain, has very little internal structure. Recall that it has the consistency of some combination of tapioca pudding and jello. Now, you think about it, your body has a lot of internal structure. So you have bones, you have muscle, tendons, skin, all meant, among other things, to provide structural support. Well, the brain has very little of that. So, given its delicate nature and its vital importance, it's perhaps not surprising that the brain is incredibly protected. Let's consider 3 examples of protection, starting from the outside in. The first layer of protection is the skull. The skull serves as the outermost layer of protection and acts as armor, shielding the brain from blunt trauma. Just below the skull are 3 membranes called meninges that serve as the second layer of protection. These meninges do several things, but importantly, they act as a buffer between the skull and the brain itself. Because while the skull is great as a shield, it's actually quite destructive if it comes in direct contact with the brain that it's trying to protect. A third way that the brain is protected is that it is bathed in cerebrospinal fluid. Now, this fluid circulates through vast cavities called ventricles that are deep inside the brain. These ventricles both cushion the brain against blows from outside, but also allow the brain to float. Now, let me say a little bit about that. Recall that the brain doesn't have a lot of internal structure. So the ventricles, you can think of them almost like balloons filled with fluid. They allow the cerebrum, for example, to sit and float, and it takes pressure off the rest of the brain. In fact, because of this lack of internal structure, without those ventricles, the brain would literally collapse under its own weight. So the ventricles play an important role both in prevention of trauma from outside and providing some measure of internal structure. The cerebrum can be broken down into 3 separate areas: the cortex, white matter, and several subcortical structures. Let's start with the cortex, which is a thin outermost layer of the cerebrum. Now, I say thin, and I mean thin. It's on average about 5 millimeters thick. And in those 5 millimeters, there are up to 6 separate horizontal layers of neurons. Now, although the cortex is thin, it's actually quite large in terms of the surface area that it covers. In fact, if stretched out, the cortex is actually the size of a large pizza box. So, given that it has to fit within the constraints of the human skull, it's not surprising that the cortex then ends up being quite convoluted, giving rise to the characteristic ridges and valleys that are so prominent when looking at a brain. Now, those ridges and valleys have formal names, of course. A ridge we call a gyrus, and any valley we call a sulcus. We'll talk more about those in subsequent chapters. One final thing that's worth mentioning about the cortex is that it's often referred to as gray matter. This is because the cortex is made up primarily of the cell bodies of neurons, which when viewed look gray, so thus we call it gray matter. Lying just below the gray matter, that is the cortex, are vast tracts of what we call white matter, which are made up primarily of myelinated axons from the neurons originating in the cortex. Now, we call the white matter because myelin is primarily made up of fat, and fat, when viewed, looks white. So therefore we have that contrast of white matter on the one hand and the gray matter of the cortex. Now, the white matter provides the communication infrastructure, allowing information from the cortex to reach both other parts of the cortex as well as the rest of the brain and the body. Perhaps the most important area of the white matter tracks is called the corpus callosum, which is a large, thick bundle of fibers right at the heart of the brain. The corpus callosum is the primary mechanism by which the two hemispheres communicate with each other. Embedded deep in the white matter tracts are several very important subcortical structures, including the basal ganglia, the amygdala, and the hippocampus. Let's start with the basal ganglia, which are paired nuclei at the base of the cerebrum. The basal ganglia are involved in several important functions, including the coordination of voluntary movement and in a process called behavioral selection. Let's talk about that last one for just a moment. The basal ganglia actually inhibit actively several motor areas of the brain, and it's not until that inhibition is released by the basal ganglia that those motor areas can ever respond to an incoming stimuli. So in this way, the basal ganglia play an essential role in helping to decide which of a range of motor responses are actually executed in response to an incoming stimulation. A second important subcortical structure is the almond-shaped amygdala, which, just like the basal ganglia, exists in a pair, one in each hemisphere. Now, the amygdala plays a very important role in several functions. Here, we're just going to focus on one, and that's the processing of fear. Interestingly enough, the amygdala has two pathways for dealing with fear, a short pathway and a long pathway. These two often work together simultaneously. The short pathway takes information from the thalamus and routes it directly to the amygdala, whereby the amygdala takes that information and triggers an emotional response that's usually of the fight or flight variety, which is meant to ready your body for survival. In contrast, the long pathway takes that same information from the thalamus and routes it to the cortex and other areas of the brain, allowing for that information to be put in its proper context and integrated with your past memories. I said they both work together, and nowhere is this more obvious than being in a movie theater. Let's imagine you're watching a scary movie and something jumps out on the screen. Now, you feel quickly that startle effect, and you do feel for a moment quite scared. But in due course, that long pathway takes over and you realize, in fact, it's just a movie. You still have the emotional response, but that long pathway stops you from getting up and running out of the theater screaming. A third important subcortical structure in the cerebrum is the hippocampus. Now again, like the amygdala and like the basal ganglia, the hippocampus actually exists as a paired structure with one in the left hemisphere and one in the right hemisphere. Most of what we know about the role of the hippocampus in memory formation comes from the study of one patient, the famous HM. HM, who unfortunately died in 2008, is widely regarded as the most studied medical patient ever, and for good reason. At the age of 9, HM developed seizures, which by late adolescence had grown so severe that surgery was needed. Unfortunately, as part of the surgery intended to stop HM seizures, surgeons also removed his hippocampus. As a consequence, HM developed what we call anterograde amnesia. That is, although he could remember almost everything back to his childhood, HM could no longer form new explicit memories. HM taught us a lot about the role of the hippocampus in memory formation, but also about different types of memories. For example, although HM couldn't form new explicit memories, he could form memories for certain procedures, that is, memory for how to do things. In this way, the study of HM taught scientists a lot about memory and about the role of the hippocampus in certain types of memory formation. Okay, to summarize, in this chapter, we covered the fourth component of the way we're organizing the brain, the cerebrum. Specifically, we introduced the cortex, that thin outermost layer of the cerebrum. We discussed those vast white matter tracts that lie right below the cortex, and we focused on three very important subcortical structures: the basal ganglia, the amygdala, and the hippocampus. In the next chapter, we'll focus on the cortex in greater depth.